Thanks for joining us with this video alternative to our Girls' Day. I'm coming to you from the Naval Academy in Annapolis, Maryland, and we are really disappointed that we won't be able to spend the day, March 21st, with you. We always look forward to our Fall and Spring Girls' Day, where we can bring together about 200 girls to celebrate opportunity, science, and engineering. So we're going to provide this with you, to you, as a little bit of an alternative. We hope you'll stay with us through the next half hour or so, and we're also going to send along some information that your teachers or your parents can print out for you. A little bit about how girls can take advantage of opportunities, take a few minutes to fill out your Bill of Rights. Also about assessing your strengths and what you could do to make the world a better place as a scientist and an engineer. And we're going to also send along some design challenges, things that you can do with very simple supplies that, again, your parents or teachers could supply to you. We're also going to introduce you to some engineers and scientists, and maybe do some demos and some hands-on activities right with you right now. So to start things off, I'm Angie Moran. I'm the STEM director here at the Naval Academy, but I'm also a mechanical materials engineer, and I've been involved in engineering for a long time. The reason why I chose to get into engineering was, as a kid, I grew up with 5 brothers, and spent a lot of time hanging out with the guys, particularly hanging out with my dad, who was a civil engineer. And I can remember the joy and wonder that we would see in everything that we went to visit, whether it would be a bridge or a tunnel or a dam, where we would look at the things that had been involved in making that structure. And so those things stuck in my mind. And so as I went into high school and college, I had the opportunity to be exposed to a lot of great women in technical history, including people like Emily Roebling and Lillian Gilbreth. Lillian, who, although she had 12 kids, managed to be the first female engineer at Purdue and the founder of industrial engineering and industrial psychology. There are a lot of women heroes in science and engineering. And today we're going to have you meet some of the women scientists and engineers, as well as a few of the men who make the Naval Academy a strong technical institution. And we hope you'll spend some time with us, learn a little bit from them, and see how scientists and engineers make the world a better place.
Hello, I'm Samar Malik. I'm a structural engineer and an associate professor of mechanical engineering at the United States Naval Academy. What I would like to share with you today is my path to becoming where I'm at now. I became an engineer primarily because I loved math and physics, and I had the best high school calculus teacher, Miss Bussey, who really showed me what I was capable of doing. But really what made me stay being an engineer is when I actually got out of college and I could see the kinds of projects I worked on. I got to work on things from naval ships to designing skyscrapers to designing art museums, installations, and that really is what has kept me in it. I love what I do. I love being able to look at a building and figure out and understand how it's supporting itself, how it's staying up, and I love sharing that with my students. What I want to show you today is very briefly tell you about shell structures. So in structural engineering, we have all kinds of structures that you've seen on bridges. You got trusses, you got arches, things like that. But what's great about a shell structure is we get additional stiffness due to its curvature. So if you take this piece of paper and you just hold it by its edge, it basically droops due to its self-weight. But if I give this paper a little bit of curvature, it can basically support itself. And that's really what a shell structure is doing. Due to its curvature, it gains not only the material stiffness, if I made this out of steel or rubber or rope, but it gets geometric stiffness. The fact that it's actually curved increases the stiffness and its load, what it's capable of carrying. So this is a larger demo to show you. If you take this shell and you imagine it though as a grid, this is what a grid shell is, and this is what I actually specialize in. And The reason why I specialize this is because when I was working as an engineer, I saw pictures of the British Museum Great Court grid shell, and there was this beautiful glass lattice structure. And I wanted to know everything about it, and I found that there wasn't any information on how it was working and its mechanics. And so I actually went back and did my PhD to study that and to write the articles that would help designers design more structures like this. So I just want to show you basically how it's made. Is you have linear flat members that on their own, you know, maybe this could support a hanging weight or so. But what we do is we take linear members, we lay them flat, and so we make them into a lattice, and then you take that lattice and you basically push it up into shape. And so you get the stiffness not just from the curvature, but the fact that the members are acting together. So if you imagine one of these members by itself, you know, wouldn't really do well supporting a book. But if I assemble them into a shell, this could very easily, even though this table is a little bit small, can support this structure. Whereas if they were flat, it would probably snap through. And so that's what I specialize in, and I really enjoy being an engineer and love teaching students about their future profession and how to enjoy it moving forward. Thank you.
Hi, I'm Sarah Durkin, and I'm a cell and molecular biologist. Growing up, I had really good science teachers, and we always did hands-on projects in my class, and I loved to learn by doing. As I grew older, I went to school to study biology, and I liked to learn how the body works, and even at the smallest level, where there are things that you can't see. And so I studied a lot of different projects, including how diseases work, and I worked on developing new medicines. So today, I want to show you a project that you can do along with me. So all you're going to need are a few things so that you can build a model of the hand. So here's what we're going to build. And we're going to use some basic supplies to understand how a tendon works. So the human hand is made up of 27 individual bones and functions using 30 muscles. So the first thing you're going to do is take the cardstock and you're going to trace your hand. And this is very easy to cut out. So I cut out a model of my hand, and then I'll show you. We're going to mark off the joints of one of the fingers. So here I marked off my joints on my index finger. And then we take the scissors and cut those into sections. The next step is to lay out those sections so that they come together again in the shape of your finger, but leave a little space in between, and you'll take your tape and you're going to tape it back together. So that's what you should have so far. The next step is to take the tendon sheaths, which we're using little bits of straw. So you can cut your straw into pieces, and you're going to tape that piece of straw to each of the finger bone pieces. Go ahead and attach one on the palm as well. So your model should look something like this. The last step you're going to do is to take a piece of ribbon, and this is going to be your tendon that you're going to thread through the pieces of straw that are your tendon sheaths as they're attached to the bone. Then you will tape that piece of tendon string to the end of your fingertip. Now you should have a working model of the tendon in your hand. This is the flexor tendon, so it's going to be able to bend your finger towards your palm. Thanks for watching today.
Hi, I'm Mark Murray. I teach here at the Naval Academy, and I teach in the Mechanical Engineering Department. I teach a couple of courses like fluid dynamics and thermodynamics. And when I was in high school, I kind of had my aha moment as far as science and engineering, because I had a physics professor who was very big into showing us physical phenomena and how we can describe them and use them in everyday life. So velocity high, pressure low, velocity low, pressure high. And I can demonstrate that in a couple different ways. If I take a piece of paper here, a thin strip of paper, and I just go ahead and hold it between my forefinger and my thumb, and I put it close to my mouth and blow on top of it, what I'll see is a general rising of that paper. And the reason that the paper is rising up is because I'm putting fast velocity on top, which means lower pressure, higher pressure on the bottom, which is pushing it up. That's going to be very similar to what you might see if you are in a shower and the shower curtain kind of chases at you, because the water is entraining some of that air to run fast. Now, another way to demonstrate that is with this little, I just have a piece of paper that I folded in half and put a couple legs on it. And if I blow underneath this paper, we'll see what happens here. Just take a straw and blow underneath the paper. What I'll see is the paper flattens out, and that's because that paper is got low pressure now running underneath it and a high pressure on top, which is going to cause it to collapse down. Now, if I'm really good, I can actually cause it to come together, and what I would do is, in this case, I would have the angle a bit smaller, and I'm going to show the same phenomenon where if I blow in between them, now the air pressure is pushing from the outside, low pressure on the inside, and it's bringing it together. And again, another way we can kind of show that is something we look at, it's something we call the Venturi effect, where again, I'm going to have fast-moving fluid by blowing in between the two tin cans, between the two aluminum cans, and that's going to create a low pressure, and the high pressure on the outside is going to bring them together. So if I come down, I just have some straws here that these things can ride on, and if I just blow in between them, what we'll see is that the cans will come together. They're not going to blow apart like one might expect, because I got high velocity fluid going in between the two cans, which means low pressure, and then the high pressure on the outside pushes them together. So again, those guys coming together. Now we can kind of show this in another way by looking at it with a ping pong ball. And if I look at this with a ping pong ball, what will happen is I'm going to take a ping pong ball, and great, I'm blowing it straight up. But what I will also see is this: when I try to push it, it wants to stay in the center of the air. Okay? So with that, what's happening is when I try to push this away from the center, the fast-moving air runs where my finger was. And that means fast-moving air on the right-hand side, means low pressure on the right-hand side, high pressure on the left-hand side, tries to push it back. Okay, now I can use that principle by go ahead and saying, I'm going to take this, and now I'm going to do a little bit of a magic trick, where what I'm going to do is I'm actually going to have the ping pong ball suspended in the flow of the air. And once again, I'm just going to be using the Bernoulli principle here, which what's occurring is when I have this flow of air here, what's going to occur is that gravity is now going to pull down on the ball. And when gravity pulls down on the ball, the faster moving air goes over the top, the slower moving air on the bottom. And so what will happen is I'll have low pressure on top, high pressure on the bottom, which will push it up, which is exactly how a wing would fly on an airplane. So, thank you.
Christine! Christine! Where are you? I'm right here. Hold on, you can see me in a second. Wow, lighting a light bulb never gets old. It's like magic. Hi, my name is Christine Maceo. I'm an electrical engineer and I also teach math. And I wanted to share with you today a little bit about how I got interested in math and science. And I can tell you that it happened about the same age, when I was the same age that you are now. It happened in 7th grade math, and it came with fractions, which is one of my favorite topics. So I had a 7th grade teacher who showed me that 1/9 as a decimal is 0.1111 repeating. 2/9 is 0.222 repeating. 3/9 is 0.333 repeating. And 3/9 can also be rewritten as 1/3. And then she posed a problem to us and said, all right, look at that pattern. And what is 9/9? And we all said, what you're probably thinking is that it's 1. But that's not following the pattern. If I follow this pattern, 9/9 would be 0.999 repeating. But it's also 1. And so she told us that 0.99999 repeating was 1 and left it at that. And that's what got me interested, because that doesn't make any sense. But it turns out it is 1. So I am here today to introduce you to a little bit of math and show you how it can be exciting, just like that is right there. So we are going to do a little exercise from the 1500s, and that exercise is called Fibonacci fish.
So you are going to participate in an activity now called Fibonacci Fish, which you can download the worksheet for from the platform. And then we're going to pause the video while you work on your activity.
So hopefully you got through that fun exercise with all of those fish and you worked through your problem. So we had stopped right here when we started talking about it. That following month, this little blue fish was still here. This little orange fish had turned purple, but we had an additional pair of fish produced by the one blue fish that was there, and so on and so on and so on. So the pattern that you should have gotten, or the number of pairs that you should have gotten, were 1, 1, 2, 3, 5, 8. And you could have continued that problem on and on, but we decided to stop at 6 months. So what we did was we created a sequence. And this is a very important sequence of numbers that has an important pattern to it. So again, I'm going to ask you to pause your tape right now and try to find that pattern. And we're back again. Now I want to point out what that pattern might be. So first of all, if I look at this number right here, 2 is equal to 1 plus 1. So I sum these two numbers here to get that one. If I look over one more number to 3, I see that 3 is the sum of those two. And that pattern continues, where your next number in your sequence comes from the sum of the two before it. That it has a special name, and it's called the Fibonacci sequence. And this might seem like a game, or it might seem like a puzzle, or just a nice coincidence, but this Fibonacci sequence is everywhere.
One of the places where you will see the Fibonacci numbers is on an everyday pineapple. If you count the number of spirals up the pineapple in one direction, you'll count 8. In the other direction, you'll count 13. Both of those are Fibonacci numbers. Another place you'll find the Fibonacci numbers is on the sunflower, one of my favorite flowers. You can see it in the spirals. In one direction, if you count the spirals, you'll count 34. In the other, you'll count 55. Both of those are also Fibonacci numbers. Those Fibonacci numbers will change if the size of the sunflower changes.
Now what I'm going to ask you to do is to take out a piece of graph paper. So what you have in front of you is a piece of graph paper, and we have already studied the Fibonacci sequence, which is 1, 1, 2, 3, 5, 8, 13, and it goes on and on and on. We are going to use these numbers here to make little squares on our graph paper. So right in the middle of your paper, we're going to start with this number, and we are going to make a square that is 1 unit by 1 unit on each side. So that's a 1 by 1 square. Then we're going to go to this number over here, and we're going to make a box right on top of it that is also 1 by 1 because our number was 1. And we're going to rotate counterclockwise and make boxes in all of these sizes. So the next one is 2. We're going to go this way, and we're going to make a 2 by 2 box right there. And we will keep going. We're going to go down here and make a 3 by 3 box. And you guys are going to finish this pattern on your own. See how far you can get. Something that you might not have known before is that if you draw a spiral through that, you can get something called a golden spiral, and that it is present in nature. Here it is superimposed on a hurricane, but you can also see it in seashells.
So I'm Elena Cimpoiascu. I am a professor here in the physics department at the US Naval Academy for about 13 years. My interest in physics started when I was in high school. I was fortunate to take a number of courses that showed me that physics actually can answer some questions that I had about how the world works, just through in a very simple and elegant way. I decided then to dig in a little deeper, and I went to the University of Bucharest in the physics department, where I graduated from with a bachelor and master's degree. After that, I traveled to the United States, and I earned my PhD in physics from Kent State University. Specialty-wise, I'm a condensed matter physicist. I'm interested in materials with special properties that can enhance, optimize the applications that we have today, or even can produce new novel applications. Talking about the properties I've been interested in, these are magnetic and electric properties. I've studied all kinds of materials like high temperature superconductors, like carbon nanotubes, heterostructures of semiconducting materials. But today, I will illustrate in a simple experiment one property of material which is actually optical, and that is the index of refraction. Well, the materials that I'll show you today interacting would be canola oil and a couple of beakers, Pyrex glass. The property we are thinking about is called the index of refraction. Index of refraction, written as N, has to do with how the rays of light are propagating through a material and the speed of the light through a material. It turns out that light travels slower in materials like glass or water or oil compared to when it travels through vacuum. Well, when a ray of light hits the interface between two materials with different indices of refraction, it will reflect and it will refract. For the light to get into our eyes so that we can see it, it definitely has to reflect or scatter off the interface. When it hits a material with an index or different index of refraction, well, if it will reflect and counter our eyes, or if the materials have the same index of refraction, let's see what happens. So it happens that the Pyrex glass and the oil have the same index of refraction. So what I'm going to do, let's see what happens if I fill the inner beaker and I'm going to let it overflow. And then we can see practically that the inner beaker disappeared. It's no magic. You can do this experiment in the kitchen. And it's only physics, and it's beautiful physics. So what happens here? Well, as the rays of light comes through, the oil hits the inner beaker. Well, the inner beaker has the same index of refraction as the oil. So the light doesn't get the cue to actually reflect and come back towards our eye to tell us that there is an interface there. So it keeps on going straight. So therefore, the inner beaker disappears. Well, this is called index matching, and it is used largely in the physics and the industry of optical fibers. Well, hope you enjoyed it. Thank you.
Hi, this is Angie Moran one more time. Thanks for spending your little bit of time with us today. Again, we're sorry we couldn't see you in person, but we hope that some of the insights and stories that we've told you about becoming an engineer or a scientist have inspired you, and we hope that you'll continue to look for opportunities. I wanted to take this opportunity to tell you a little bit more about being a mechanical and materials engineer, and particularly about the fact that what I found the most inspiring is that I've had an opportunity to design and create and build things. And so we're going to ask your teachers or your parents to share with you a build opportunity. You can either build a Mars lander or a catapult and try to improve upon it, just like an engineer would try to improve upon something that needed betterment. Mechanical engineers do get an opportunity on a regular basis to design sometimes new things, but often to improve upon existing processes or products and make things better for those throughout the world. So let me show you how to build a catapult real quick. This is our final product. We're going to take popsicle sticks. I have some nice, bright, big, colorful ones, 7 to begin. Wrap one end with a rubber band. Wrap the other end nice and tight with a second rubber band. That's created your wedge, a simple machine. Take 2 more, wrap them together with an additional rubber band so that you now have created a lever. Put your wedge in place. You may want to attach your spoon prior to including your wedge. I'll do that now just for an alternative way from what your directions may say. So once my spoon is attached, and again, you want to make those rubber bands nice and tight, I add the wedge. This is the only tricky part, and you need to be a little bit dexterous. Take another rubber band, cross it at an angle where the 2 pieces intersect, and to keep it stabilized and in place and as tight as you can, a final rubber band along the opposite diagonal, and push that in nice and tight. And now you have the catapult. So you can add projectiles and launch. Right? And last but not least, it wouldn't be a girls' event without something that may come into the category of don't do this at home. Have to have at least one. So I wanted to add a little bit more to the concepts of aerodynamics and fluid dynamics that Mark Murray talked to you a little bit about, and talk to you about the concept of vortices. We see this sometimes when we do our storm chasing modules here at Girls' Day. We couldn't share that with you today, sorry, that's a little difficult to do virtually, but you've seen a tornado in a bottle, okay? The spinning water causes a vortices. The air is fed through the tube and drops into the container below. Do that one more time. Okay, that's cute, but maybe not too exciting. How about a fire tornado? Let's do that one. Okay, here we go. There we go. Now that is a fire tornado. That actually happens in real life. Anyway, thanks for being with us.